When is he coming back?
He was sick this morning. He'll be back Monday. No, his girlfriend said he woke up puking.
Okay. All right. So what we're going to do is we're going to go through kind of 3 different equations that allow you to keep track of this object in terms of position, in terms of velocity, in terms of energy. So you should have done through number 8. So here's what, when you look at that equation, period equals 2 pi times the square root of m over k. So one of the things that you have to develop the ability to do is see what is a factor and what is not a factor. So when I make this spring oscillate, there's only 2 things that determine the value of that value of period. The mass on the end of the spring and the value of k. That's it. So whether it's oscillating like this, okay, with a very small amplitude, or if it's oscillating like that, doesn't make any difference. The value of that amplitude has no impact whatsoever on the period of that oscillation. Okay? Now, but if I change that amplitude, what it does change is that it changes how fast it moves. It changes its energy. It changes the kinetic energy. It changes a whole bunch of different things. So you have to have the ability to look at an equation and go, what's important and what's not. Now, a lot of times you want to talk about frequency, because frequency is going to be part and parcel of the same discussion. So if you look at period equaling 1 over frequency. So if you go through this process and go, okay, well, let's take the inverse of this. So then if you come in here and go, okay, that's going to be, if I'm going to talk about the frequency, right, which is going to be 1 over period, then I'm going to take the inverse of this whole thing. So I'm going to take 1 over 2 pi times the square root of m over k. Well, since that's underneath the radical, I can write that as 1 over 2 pi times the square root of k over m. So if you look at what's going to happen now, this is why these are inverses of each other. So even if you look at this in terms of the units, that k value is newtons per meter, okay? That's going to be mass, which is going to be kilograms. So your newtons are kilograms meters per second squared, divided by meters divided by kilograms. The kilograms cancels out. The meters cancel out. You're taking the square root of 1 over second squared. You get 1 over seconds. That's what frequency is measured in. Okay? So, but again, look at what's going to happen. So if I come up here to this, and let's say, for example, instead of just 1 kilogram, let's say that let's say I put a bigger mass on there. If I put a bigger mass on there, what's going to happen to the value of period? It's going to get bigger. Okay, so you're going to see this take longer to oscillate. Okay, but period is going to take longer. But then what's going to happen if you come down here? Because if you talk about frequency, which is k over m, if I increase the mass, then what's going to happen to the frequency? It's going to become smaller. So if I put more mass on there, this is going to take longer to oscillate, but then you won't have as many vibrations per second. Okay, so this is why those are like inverses of each other. Now, when you get to number 9, I'm going to show you a couple of different ways that you can approach number 9. Okay? So you've got x equals a cosine 2 pi little t over t. This is the only time I will tell you that your calculator has to be in radian mode. Okay? This doesn't work in degrees. This has to be in radian mode. Now, radians are typically associated with circular motion. So here's how motions on a spring match up with motions on a circle. And you'd think, how does that have anything to do with a circular path? Well, here's the best visual. imagine that instead of oscillating up and down, imagine that you put that thing on a spring and you have it oscillate back and forth horizontally. Okay, it's going back and forth like this. So have that visualization. This thing is going back and forth like this. Okay. Situation number 2, you have a turntable like in a microwave, and you put a cup on that turntable, and all you're watching is the sides. Okay, you're not looking down, you can't see anything. The only thing you can see is the side. So what you're going to see is that you're going to see that cup go to one side, and you're going to see it come back to the other. Go to one side and back to the other. Just like you would see that mass on that spring oscillate, go back and forth and back and forth. So if all you see, if that's all you can see is a horizontal motion, you don't know if it's oscillating on a spring, or you don't know if it's on a turntable and that turntable is spinning around. You can't tell the difference. It would look exactly the same. So this is why circular motion matches up with harmonic motion, because from a side perspective, you can't tell the difference. All right. So there's a couple of ways that you can do this. It's a personal preference thing. What we're going to try and figure out is we're going to try and figure out where the position is of this oscillating spring at different points. There's a smash mouth approach to this, and there's an elegant approach to this. Okay, I'm going to show you both. How you do this is up to you. Okay, doesn't make no difference. So, Gracie, what was the value when you guys did that and you oscillated? You timed 5 oscillations. So, what was that value of period?
1.04.
Okay, so 1.04 seconds. So here's the smash mouth approach. So the smash mouth approach is Gracie is going to come in here and she's going to actually put in 1.04 seconds. Okay, that's going to be this value of t. So what we're going to look at is different values of time. The 1.04 isn't going to change because that's the value for that particular spring. Okay, 1.04 seconds. So no matter what I do with little t, I'm not going to change that value of big T. So Gracie's group is 1.04 seconds. That's that value of capital T. So at time 0, and let's make sure everybody's cool with how this is going to play out in terms of your calculation. So you're going to have your amplitude, and on this one, so that it's going to make it easy for me to grade, I'm going to assume that your amplitude is 5 centimeters, okay? Which is about like yay, which is typically about what you all did. So that's where I got the 5 centimeters from. So if you look at this equation, you're going to have 5 centimeters, which is 0.05 meters. That's your amplitude. That's a fixed value, okay? It's not going to change. That's your amplitude, boom, 0.05. Then you have the cosine. Now, if you're doing smash mouth physics, okay, Gracie's going to come in here and go, that's going to be 2 pi, and the 2 pi comes from the correlation between horizontal motion and angular motion. That's where the 2 pi comes from. Because if you already harken back to, remember when we did angular rotation? Anybody remember how many radians there are in one revolution? 2 pi. That's where that 2 pi comes from. Okay? Because if imagine that cup going around, if it made one revolution, it would travel through 2 pi radians. That's where that comes from. Okay? So if you're Gracie, I'm going to tell you, hey, at time equals 0. So she's going to put in 0 seconds, and then she's going to divide that by 1.04 seconds. So if Gracie likes smash mouth physics, this is what she's going to do. Now, you're going to be taking the cosine of, fundamentally, what are you taking the cosine of? 0. Cosine of 0 is 1. So at time 0, cosine of 0 is 1. Guess what? You get a position of 0.05 because that's your amplitude. Okay? So this is why, Morello, on your position time graph, okay, this is why you're going to start up there at 0.05 meters. Okay? Because at time 0, that's where that is. Okay? Now, next thing you want to figure out is where is it at t over 2. So on the smash mouth physics, if you're into that, you can take 0.05 meters times the cosine of 2 pi. Now, this is going to be at half the oscillation, t over 2. So if you're Gracie, she's going to take half of 1.04. So if you take half of 1.04, you get 0.52 seconds divided by 1.04 seconds. So if you're into smash mouth physics, you're going to take 0.52 divided by 1.04, multiply that by 2 pi, take the cosine of that, multiply that by 0.05. Okay? If you're into smash mouth physics. Okay? Now, if you're into the more elegant side of this, like, Burkamp, I love the elegance of mathematics. And there is a certain beauty that exists in mathematics if you go deep enough beyond just 2 plus 2 is 4. So if you get into the more elegant side of this, you're going to take 0.05 meters times the cosine of 2 pi. Now, instead of little t, here's the key substitution. Instead of little t, I'm going to put t over 2, okay, divided by t. Now, in that situation, because I have uppercase T, and then I've got the t down below, what's going to happen to my value of t? It's going to cancel out. So then I'm taking 2 pi times 1 over 2, which reduces down to taking the cosine of pi. And what's the cosine of pi?
Negative 1.
Negative 1.
Oh my gosh, I knew that right off the top of my head.
That's what I was thinking.
That is so
So
embarrassing.
this is why, when you go to that graph, when you're at, there's t over 2, okay, and there's 1/4, this is why you're down here at this point, and why it does this. So now, when you go to t, okay, and again, this is actually, it's easier if you approach it from a more elegant standpoint, because then you have 0.05 meters times 2 pi times t over t. T over t reduces down to 1. You're taking the cosine of 1, which is, or you're taking the cosine of 2 pi. Cosine of 2 pi is positive 1. You're back to 0.05 meters. So on number 9, you should see you're going from 0.05 to negative 0.05 to positive 0.05, which is why your position time graph looks like this.
I was like, why are we doing this? They're all the
That's
same.
why there's a method to my madness, dear. Louis, talk to me.
Can you explain conceptually how frequency is the inverse of period?
Yeah, I can show you. You got a rubber stopper, right? If you, this is going relatively slowly. Okay, so if you were to measure that time, so here's all I want you to do, Louis. I just want you to go like 1001, 1002. I want you to count how long it takes for it to go around, just using 1001, 1002. Right? You ready? Let me know.
1001, 1002, about 1002.
About 2 seconds, let's say. Okay? 1001, 1002. Right? Okay? Now, then if you count that frequency, okay, you're counting, now you look at this and go, okay, there's 1, 2, 3, 4. So that rubber stopper isn't going past you very often. Okay, so the frequency is going to be a lower value because of the fact that it's taking so long for it to go around.
Yeah.
Now I'm going to do this. Okay, now I want you to try and count how long it takes to go around one time.
1,000. Yeah, like 1,000.
Now,
Like half
Okay.
hour, yeah.
right? Now, so what's happened to the value of period?
It's gone down.
It's gone down. But now, what's going to happen to the number of times it goes past you?
It's gonna speed up.
It's going to speed up. So that's why those are inverses of each other.
Okay.
So the less time it takes for it to go around,
The
the
more,
more times it's going to go past you. Okay? Does that make sense? Okay. Now, when you get to number 10, okay, so when you get to number 10, and this is if you like need this equation, I will give you this equation on the test. Don't memorize it. But hopefully you can look at this and say, oh, this makes sense. So this is V max equals 2 pi f times your amplitude. Okay? Now, think about this. Any good equation works under any circumstance. If this is sitting here right now, okay, let's just look at this. What's my V max going to be right now? 0. Why? There's no amplitude. Okay?
Oh.
Right? So if I have no amplitude, I have no V max. Makes sense. Okay? Now, if I make it oscillate, okay, now it has an amplitude. So the frequency is a fixed value based upon whatever the spring is. So if you look at this calculation of Vmax, so like if I'm Gracie, her frequency is going to be like 1.05. And that's going to be 1.05, and this is where you have to pay attention to the units. Frequency can either be expressed as s to the negative 1, or you can write it as 1.05 times 1 over seconds, okay, because it's frequency. It's an event per unit of time. Now, when I multiply that by my amplitude, look what happens with the units. I've got meters times 1 over seconds. I get units of meters per second. Boom. There's my Vmax, okay? So, clearly, and you can just make this observation, if I pull this down even farther and I increase that amplitude, what's going to happen to the value of Vmax? It's going to go up because of the fact that you're storing more spring energy, you're storing more gravitational potential energy, therefore you're going to have more kinetic energy in the system. So, here's what I want you to see. If you look at that equation for period equaling 2 pi times the square root of m over k, is amplitude a factor in the period of the oscillation? Nothing to do with it. Is amplitude a factor in your Vmax calculation?
Yes.
Yes. So in some of these amplitude is a factor, and some of these it's not. And that's one of the things that you have to be able to look at and say, okay, hey, what's important? Now, but is K a factor in your Vmax?
No.
No. But where K is a factor, K becomes a factor when you look at the frequency. Because K determines the frequency, that then impacts your Vmax. Okay? So K isn't directly in there, but it's a factor because it influences the frequency of the oscillation. Sam?
On this problem, do we gotta change our frequency from revolutions per second to radians per second?
No. It's just because it's just whatever you had for that frequency on page 1.
Yeah. Okay.
Yeah. Because you don't want that in radians. It's just your frequency. That's it. Yeah.
Cool.
That's it.
Solid.
Solid. That's it. So typically that on that answer to number 10, typically that's around 0.3 meters per second. Okay, that's an ish, but it's somewhere around in there. Now, then you want to calculate the kinetic energy. So your kinetic energy is going to be 1/2 mv squared. So what you're doing is you're calculating your maximum kinetic energy.
Would
Pop.
you say that number 10 is supposed to be around?
Number what?
0.3? Yeah. Okay.
On 10?
Yeah.
Yeah.
Okay.
It's an ish depending upon what your spring is, but it's usually something around there.
0.3%.
Yeah.
That's spring's the best, but that other spring that you chose was pretty good.
That one looks crazy.
That
The
one
one
was
that's
really
like
bad.
half open, half it's just stretched.
Now, so when you get to question number 13, okay? So with that one, and again, this is kind of the cool thing about this. Ask me if you have a question.
Does the frequency stay constant regardless of the amplitude?
Just because here's the reason why. If you look it up here, it doesn't impact period, so therefore it doesn't impact frequency. But when you have a bigger amplitude, it has to travel faster to complete that in the same amount of time. So that's why it impacts your Vmax and why it impacts your energy. Okay? Now, so when you get to question number 13, I say it explains in terms of potential and kinetic energy. So as this thing oscillates, what are the two types of potential energy you're going to have? Ugg and spring. So as you increase that amplitude, you're going to have a bigger change in Ugg because you're going to have a bigger change in height. And you're going to have a bigger change in us because you're going to have more elongation. So that's what I'm looking for in terms of that explanation. So give you some time, finish up through the bottom of page 3.
Okay.
It's 0.9 and 5.
You know that? Okay.
Just checking, we don't want you to fall behind. Do you get 0.02?
For what?
Oh, don't hand that in.
Oh, no.
Oh, there's much more to go.
Yeah.
Yeah, I was gonna say, I was like, I thought you said we had 2 days to do this.
Oh, yeah. Oh, no, that's just
We got like
that's
part-
just 1/3
What?
of the
Oh
lab.
my.
Is this just kind of like a review, or is
No,
this
this
getting us
is
into
nothing. Beginning of
what is
waves.
this, beginning of waves and stuff?
Yeah, it's just the beginning
Okay.
of
We're done
waves.
with first semester.
So like,
That's a different
none of
class.
that stuff from the first semester will be in this class at all, or will it?
Like the
Not
base-
really.
Not really.
In other words, will this class be any
Like
different
this.
at all?
This is the most you're gonna get.
We are, like, for
No
example,
more
we're gonna
gravitational
tie,
motion.
like gravitational forces in with magnetic forces.
Oh.
Like if I want to say, I want to make something levitate, how much magnetic force does it require to balance out the gravitational force?
Okay.
When we talk about electrons moving in a magnetic field, we're gonna set the magnetic force equal to the centripetal force.
Okay. As long as we don't have to do like Lagrange points or something like that.
No.
Lagrange?
No.
Lagrange points.
What did you say?
I know.
One second.
How rude.
Why couldn't we just round up to 10? If people, we should just go.
Well, if the Earth
We
had
should
been a
have just
little
used
bit
10.
more
That would have
massive,
been so much easier.
if the Earth had been a little bit more massive,
We get hit by enough asteroids.
Yeah.
or if me would have been a little bit smaller,
Can we just like compress it a little bit? I mean, like, you know.
Someone break into that vault and change the length.
change that length.
Or change the gram. Just make it tiny.
Are you sure you know how to write this at the middle?
What?
How do you describe like the middle of the oscillation?
If it's going up or down.
Equilibrium. Oh, you're so smart, Gracie. What did you say?
This becomes 0. This is 2 pi times 2.
What's the US?
What did you say for
US
us?
equation?
This becomes 0.
It's elongation.
It's like one.
Yeah.
What do you say for us? Like, what happens when you increase the amplitude for us?
This is 1 pi.
What are they walking through?
And it's -1. I don't care.
The one you
Yeah, I put that. And then for us, I said us would increase because the elongation would also increase, which also increases the total energy of the system.
What did you say?
And then obviously law of conservation of energy. That
Yeah.
makes
Does pi gravitational and spring and
Does that make sense?
Kind of have it about.
Yeah.
Like enough
Why
sense?
just
we're making amplitude fluxes.
Oh, should I pause this?
T is
Yeah.
just
Okay, so now we're gonna take this, so now we figured out what position looks like, now we figured out what velocity looks like. So now that we have that Vmax, now we're gonna use this equation. And all this is a function of, it's a function equation that expresses what your velocity is as a value of time. So you have your V max, okay? And there's a reason that there was a negative sign in front of that because it's going to make kind of everything work out. So here's the story. So you're going to use your V max, whatever you had from the previous page, okay? So that's going to be different depending on what you have, okay? Everybody's going to be a little bit different. But again, it's going to be something around 0.3. So again, you have to be in radian mode. And again, there's two options on how you can do this. You can either do the smash mouth physics approach, or you can put in the actual more elegant approach where you use T. So no matter what, let's look at this. At time 0, right? What's the sign of 0?
A 1, right? 1.
It's,
Oh, wait.
0.
Sine of
Is it
zero.
0?
Cosine of 0.
Sine of 0 is
Zero.
0.
Cosine
Okay.
of 0 is 1.
Sine of 0.
Why?
Right? If you don't believe me, punch it in
Oh,
your
0
calculator.
degrees.
Make sure we get a
Okay.
radian mode.
Look at your unit circle.
Okay? So here's the story. So this is why on your
memorizing.
velocity time graph,
Play catch up.
right? Where does your velocity time graph start? Starts at 0. Because if you use this equation, then you're taking the sine of 0, which is going to be 0. So you're taking 0 times your negative V max. Oddly enough, you're going to get 0. Now, here's the bigger picture in terms of if you're a math nerd. So your position time graph started like this. So where that position time graph starts, if you drew that tangent line, that's going to have us, no.
They don't look bad on them.
I'm not disputing that, but it just looks a little bit weird.
Oh,
So
It's too bright.
at time 0, if you drew that tangent line, that's going to have a slope of 0, which is why your velocity time graph starts at 0, because the slope of your position time graph's tangent line is 0. That's why that velocity goes to 0. Now, when you get to 1/4 t, here's your options. So you're going to have your negative V max, which is going to be about negative 0.3 meters per second, whatever that is, times the sine of 2 pi. Now, if you were to do smash mouth physics, if you're Gracie, you're going to take 1.04 seconds, you're going to divide that by 4, and then you're going to divide that by 1.04 seconds because you want 1/4 t. So if you're into smash mouth physics, take period, divide that by 4, multiply that by 2 pi, divide all of that by 1.04, take the sine of that, multiply that by negative 0.3. If you're into smash mouth physics, you like that, it's cool. Mr. Burkamp, I love punching numbers into a calculator. Good for you. Happy for you. Fantastic. However, if you want the more elegant approach again, you're taking the sine of 2 pi times t over 4 divided by t. Gracie? Not Gracie. Morella?
Wow.
Sorry.
I have a question. Do we need to do this on another piece of paper? Or
No.
can we just squeeze it in there?
Yeah. All I have to see is just one calculation.
Oh, 1?
Yeah, because all you're doing is just plugging the same numbers in.
Okay.
Now, but here's, if you go with a more elegant approach. The t's cancel out, okay? And then you've got 2 pi over 4, which reduces to pi over 2. Okay? So then, if you do this, then you're taking the sine of pi over 2 times negative 0.3. Voila, there's your new velocity. So I don't care how you do it. Smash mouth, the more elegant approach, it's up to you. But go ahead and go all the way through. That's going to get you through number 5.
Big chillin'.
Why does O? It's non-increasing.
It's gonna be increased because if the amplitude's bigger, right, then you have to lift it up a little higher. Still the same.
Oh, okay, my bad, I mixed
Yeah,
up,
'cause
I
I'm
mixed
not
up us
seeing
and
it.
UG, I was like, we're not.
I think Louis kind of fallen behind here. He's still on the white page.
Papa Jake, that's why you were, that's why you were late.
Did you work to number 8
That's why you were,
yesterday?
that's why you were late to class.
Did you work to number 8?
I did,
You did?
I did. Were you on time to class today, Pop?
Valid point.
No.
Did you get lost BPS? Yeah, I got lost again.
Yeah, you
Whatever.
lost with the
Listen,
shoulder
shut up.
it's the
back of
beginning of
line.
the year
How did-
again.
It was a line at it was a line at Jersey Mike's.
How did you even get your
You
girlfriend in
snitched.
Jersey? I did
You
snitch.
snitched.
I'm still salty about my
God.
calculator.
It took
I'm
you
still
2 seconds to
salty.
realize that.
Someone got a new one.
This dude.
I gotta staple this. I haven't stapled this yet.
Pop, I'm not a stickler for rules, but technically you're not supposed to, stop in between.
Well, you
Oh.
left her at sea lunch. So
You-
it's,
What's 1.04 times 0.5?
You go to the lunchroom at all?
Yeah,
Yeah, yeah.
you have a
Okay,
calculator in your hand.
so-
It's
Listen,
0.26.
why?
Oh,
You
what?
wanna look at the lineup
1.04 times
food we have
5.5?
here?
Oh,
Oh, I know.
I don't have third
Oh,
grade.
sorry.
But they got to class on
Sam,
time.
eating
The
hot
other
sauce
class
over there.
early.
What is that?
Jersey
That's no.
Mike's.
Why do you have barbecue sauce?
Him? Oh, he
Yeah.
had,
Cause Sam's ham, alright?
I was having chicken. I wanted, yeah.
Jenna, what'd you get for the
Did you
second
get your
one?
lettuce and the barbecue sauces?
Not this time.
I used to be able to eat barbecue sauce.
Wait, why is there a negative sign?
Barbecue sauce is
Because
good.
it's carrot.
Negative.
dude, that
Oh
was
my
so
god,
funny.
I'm an idiot. Never mind. And this is not right. Don't look at that.
I was like, there's no way this.
I didn't
guy
use this sign.
Brother, did you stop the camera?
Yeah, I was gonna say.
Oh, let me do this.
I was gonna say.
Where we're at through
No.
number 5.
No.
Number 3 is.
Yeah, we're on number 3.
I thought you
You
just
just
explained
explained
I did. I just explained number 3.
Oh, tangent lines.
Yes.
the derivative.
The slopes of the tangent lines on the position time graph gives you your instantaneous velocity.
But it's talking about amplitude time. Oh, but that is position?
Yeah, the amplitude time graph is the same as your position time graph.
Alright. That makes sense.
Why don't we give a calculus physics? I don't-
Because there'll be so few people that have
It's
had
not
enough
even taking
That's
calculus.
engineering physics, right?
Do you have to have
If
calc
you
2?
do
Take
calculus
calc
physics
physics?
and engineering physics.
Theoretically, you can just have calc 1. But it's, the more calculus you have, the easier calculus-based physics is. So, that's why we don't offer it, because there'd only probably be maybe 3 or 4 kids
Yeah.
that would be in that, and they're not gonna offer it in that class.
Wait, what block is it? First.
We definitely.
Okay,
Well, I had to get English. And
Now.
I had to get speech too. And then I have this at 80 bucks.
let's talk about this equation on number 6, okay? So what we figured out is how we can calculate Vmax, okay? And so if you look at how you calculated Vmax, that's a function of amplitude. When you calculate Amax, which is gonna be your maximum acceleration, okay? And x is gonna be the position at time 0. So here's what I want you to see, is that Amax, if you want to get that value, you have negative k over m. So when you look at this, this is why I started you off on question number 1. So when you look at this, this is the importance of the sign. If you go to your acceleration time graph, so let's kind of work backwards. Where does your acceleration time graph start? At 0, positive value, or negative value?
Negative.
Or negative.
Negative.
Yeah, negative.
So your acceleration time graph is going to start down here at some negative value, right? And again, understand how these pieces fit together. You're going to start off with your your biggest negative acceleration. Because when it's up here at the top, okay, this is what you have to understand. As this thing starts to fall, your gravitational force is going to remain constant. That isn't going to change. So when you're up there at the top, you have your minimum upward force from the spring. Because the force from the spring is F equals kx. So when you're up at the top, you have your minimum upward force from the spring, and you have a large gravitational force pulling down. So when it crosses the middle, your acceleration is 0, because that's when the two forces from the spring and the downward pull of gravity balance out. Once you cross that threshold in the middle, then the force from the spring gets bigger, then your gravitational pull, now your net force is acting up, and it begins to slow down. So when you're up there at the top, and here, this is why this graph has to start up there with a positive x value for all of these things to work out. So when this thing begins to fall, you have negative velocity, you're speeding up, and you're going to have negative acceleration, because that's when you have your biggest net force. So your biggest net force is either going to be at the top of the oscillation or at the bottom of the oscillation. So this is why your acceleration time graph starts with a big negative value. So that's why you have to have that negative sign out in front of this. So if you think about this for just a second, if you want your maximum acceleration, your x value is going to be your amplitude, because your amplitude is going to be your maximum distortion from where you started. Okay, so when you have that, when you're up at the top or when you're at the bottom, that's when you have your biggest acceleration, and that's when you're at your amplitude. So we could come in here instead of x, we could put amplitude, because that's when that's going to take place. So what you want to do on number 6, and this is going to vary greatly depending upon your k value, okay? So you've got your k value, whatever that is, okay, and go off the one off your slope, okay? Go the one off the graph. You know your mass, and your amplitude is going to be, and you can just go ahead and use that 0.05 meters. If you didn't write down your amplitude from yesterday, just use 0.05 meters, okay? So that way kind of everybody's consistent. And that's going to vary greatly. That answer to number 6 is going to change greatly depending upon your k value. But typically it's around -2. Okay? That's a huge ish depending upon your k value.
Which K value? The calculated one?
Yes, that you got from your tangent line. Or not this, not your tangent line.
Wait, we're using the experimental test?
No, that's the one from the slope.
So experimental?
So that's a 70?
So from the.
Yeah, or whatever
From the
whatever
best.
the slope is.
So not the theoretical.
The experimental.
That would be your experimental, right? Oh, wrong number. Wait. 756.5.
Position it.
You plug in this for the little two. Which one doesn't work?
Okay, so yes, I have.
I got 2.3.
Wait, so is it plus or minus?
Hold on, I got a.
I know.
I got minus.
Amplitude.
Did you get 2.333?
Yeah.
The maximum acceleration.
Wait, what'd you get?
I got negative 1.82.
kilograms.
Okay, yeah, 1.88.
Is it 2 point
Why do you do kilograms meters per second?
just meters per second?
Why would you even put kilograms?
Well, I was just like, I was just reading it out loud.
That is
You know?
not triple.
The kilograms delete. Wow. You did 1.5 kg.
Oh, because it's acceleration.
1.5 kg.
Yes, sir. And then times 0.05.
I don't know where we got that from.
What do you mean by explain the beginning point of the acceleration?
Like, why does it start here?
Because you said use that one.
You can explain it in terms of forces, that's the easiest. Because you're starting at the top of the oscillation.
Mhm.
So you have your smallest upward force from the spring relative to the gravitational force. So your biggest net force is pointing downward, and that's why you have your biggest negative acceleration.
Okay.
That's the easiest way to explain it.
So you're confused.
How is that 2.2?
But you not get to,
What do you
Does
mean?
this make sense?
what'd you put for the other, for the A, for X?
For X 0.05. Well, no, I understand that, but why is is it because it already has spring tension on it? Is that why?
Okay. So we get to number 8. Now we're going to calculate acceleration as a function of time, and we'll see how that changes. Now, don't get confused on this one. When I type this up, I put that negative A max in there because your acceleration is already negative. So don't put that as like a negative of a negative, okay? I just put that there because I knew your acceleration was already going to be a negative value, okay? So don't make that a negative of a negative. I actually, and it's ironically, I put that in there to make it simple, and then kids got confused, like, oh my God, it's a negative of a negative. No. All I just put there, just say, hey, you have a negative acceleration, okay? But it's the same idea. So, at time equals 0, you're taking the cosine of 0. What's the cosine of 0? 1. So, at time equals 0, cosine of that is 1. Your acceleration is just whatever your A max is, which is why your acceleration time graph starts down there at a negative value, okay? So that's why I don't want you get confused and go, oh, that's a negative of a negative. All you should see is that when you plug this in, you should get that maximum negative acceleration, okay? And then you're just going to look at how it's going to change. So you can either do the smash mouth physics, or you can look at your acceleration time graph and figure out, oh, what's my acceleration at these points? So you can either mathematically figure it out, or just look at your acceleration time graph, okay? But what you should see is that all of your answers on number 8 are either your maximum acceleration, either being positive or negative, or 0. So I didn't put anything weird like, 1/3 t or something like that, okay? Now, when you get to number 9, I don't want the numeric values. All I want is the net force positive, negative, or 0. So oddly enough, if you have a negative acceleration on number 8, what's the sign of your net force? Negative. Okay, do not make number 9 complicated. Now, what you want to do on number 10. On number 10, you have to go back onto your acceleration time graph okay? Or excuse me, on your velocity time graph, and indicate if the sign of the acceleration is positive or negative, okay? So your velocity time graph is going to start at 0 and it's going to do this. So basically, remember that the slopes of your position time graph, of your velocity time graph, are your accelerations. So if you want to think this through and go, oh, look, I have negative velocity and I'm speeding up, I'm going to have negative acceleration. If you want to look at your function equations and go, oh, I'm going to generate negative values. I don't care what you do. But what you want to do on that velocity time graph is go back and clearly indicate what's the sign of that acceleration in each segment on your velocity time graph. Okay? So go to that. Then what you're going to do on number 11, you're going to go to that same velocity time graph, and you're going to draw tangent lines at 1/4 t and 3/4 t. You're going to draw tangent lines, okay? Clearly draw them so I can see that you drew them, okay? Then explain how that correlates with what's happening on your acceleration time graph.
This is a lot. Stop.
Yeah, that's why I said.
Oh, we're moving? What? Oh dear. That's tragic. Oh, fidget. Wait, oh, I forget. This is our old physics class. Are you sitting, where's it at?
Right here.
Like from here?
Yeah.
Like this is fine? Front row seats.
See this move.
Wait, 1 second. Okay, let me back
Okay.
this up.
So when you talk
man.
about how you can measure the weight of something,
That doesn't.
so one option
What do you
is
mean?
that you measure what's known as your gravitational weight.
Oh.
So here I have a 0.5 kilogram mass. I'm going to hook that up to a scale. Oddly enough, it reads exactly 4.90 newtons because it's a half a kilogram. Now, here's the problem. If I'm in deep, deep, deep space, or I'm in a state of free fall and orbit around the Earth, and I try and do that, guess what? It's not going to work because there's no effective gravitational field for it to interact with. So what you can also get into is what's known as inertial mass. So inertial mass is true no matter where you are because it's only dependent upon the resistance to a change in the velocity. So basically, the more stuff something has, which is a highly imprecise term, the harder it is to get it to move, but the harder it is to get it to stop. So what I have here is like a horizontal spring. So I move this back and forth, give it a little push, right, and it begins to oscillate. Now, if I take this and put that in there, then when I do this, what happens to the period of the oscillation?
Longer.
So if I take that out, I do this, put that in there, right? So it takes longer for it to oscillate, so what's going to happen to the frequency? So if you look at the equation for a spring, period equals 2 pi times the square root of m over k. Notice that is not dependent upon a gravitational field. So if I can set this up, and I can measure the period of the oscillation, and I know the value of k, I can measure the mass of this object. Now, if I take that out and put on even more mass, now when I do this, it becomes even slower. So if I'm in space, and that becomes a challenge, like how do you monitor the weight of your astronauts in space? Well, bathroom scale isn't going to do you any good. So what you have to do is you look at it as their inertia. So if an astronaut is losing weight, what's going to happen to their inertia?
Decrease.
It's going to decrease, okay? If they're gaining weight, their inertia is going to increase. And so that's the difference between inertial mass and gravitational mass. So gravitational values are based upon the interaction with a gravitational field. Inertial mass is a resistance to a change in its velocity. Okay? Got that. All right, back we go. when you get to question number 12, okay, where it says, how is gravitational mass different from inertial mass? So that's the simple answer. So gravitational mass is based upon the interaction with the gravitational field, okay? But inertial mass is just basically a measure of its resistance to a change in velocity. So when you get to, on this backside, and here's what I want you to get through. I want you to get through question number 13, which is on that backside on that one. We're going to go to the International Space Station. I'm going to give you a chunk of iron. And you want to figure out the value of that mass. So what you're going to have is something like I just set up. So what you want to do on question number 13 is explain it in terms of the idea that t equals 2 pi times the square root of m over k. What could you measure, right? What could you measure, and then how could you use that in terms of this equation to determine the mass of that chunk of iron? So by Monday, get through question number 13, and then we'll finish the rest of that, and then we'll have the third part on Monday. So your only quote assignment is to work through number 13. Okay?
No, it was.
Nah, because I read what
Yes,
they
sir.
gave.
Yes, sir. We got Sam in here now.
The adventures of
Say hi
somebody.
to Vitor.
What up, Vitor?
Yes, sir, Vitor. Get better.
Nah, it was,
I'll see you on Wednesday. I'll see you on Wednesday.
We're gonna do a fit check real quick.
Fit check?
Fit check.
Oh yeah? Fit check. Ooh. Okay, hold on. Now you gotta sweat.
Look at this man.
I don't know.
Yes, sir. Get Connor. Get
I'm
Connor.
so
Get Connor.
internet.
Woo! Got the
Oh yeah. this
works
is
on.
good.
Oh, okay.
Let's go. Alright, let's go team.
Bye, have a great weekend.